do Norte. So he's very well known for his contribution in complex networks, neuroscience, ecology. You know you all know his contribution Levy flight search patterns. So it's without further ado, let's give the floor to Gandhi for his talk.
Thank you, Pietro. Good morning, everybody. Thank you for coming. I would like to thank the organizers, the other organizers who did most of the work. So I'm going to be talking a little bit about graph enumeration. And this is a tricky problem on the non-planar lattices. And I will show that sometimes to count polygons, it seems to be necessary to count hypergraphs. I'm not a network science person. That's not my main field. However, to show how network science has just become a major field, my most cited paper is this network science paper done in collaboration with local neuroscientists at the Brain Institute in our university. I would have liked to talk about this topic. However, we are only now starting to use hypergraphs to study these brain images. So I decided to talk about a different topic, which does include hypergraphs. So what I'm going to be talking about has been published in the last few years. I'll be speaking mainly about this paper about polygon enumeration that was published. These two papers were published in the last 2 years. So I'm going to introduce the problem and the motivation, which is how to count polygons on different kinds of regular lattices. And then I will give a brief review of the method of Grassmann variables, which are anti-commuting variables, and their integrals, which are known as Berezin integrals, and sometimes are also known as fermionic path integrals, and they're very useful to do exact enumeration. And I will present some older results of polygon enumeration in 2 dimensions, and then I will show you recent results of mine regarding 3D polygon enumeration, followed by a conclusion. So the problem is, how do you count polygons? And more specifically, how do you count polygons on regular lattices? Now, polygons on regular lattices, we can draw all kinds of polygons. For our purposes, for the purpose of this talk, a polygon is a graph, all of whose nodes have degree 2. So you have one incoming edge and one outgoing edge at each node. And the edges only connect the nearest neighbor nodes on a lattice. Now, sometimes you can have sets of polygons, so multiple polygons that might be connected or disconnected, and some papers in the literature use this term multi-polygons, which are graphs, all of whose nodes have even degree, and all of whose edges connect nearest neighbors. So I'll be counting polygons and multi-polygons on regular lattices. Why is this problem interesting? So historically, people began to study these problems because they have a connection with important problems in statistical mechanics. For example, the solution of the Ising model on regular lattices is connected to the enumeration of polygons. These problems can be very challenging. So for example, in the case of the 3D simple cubic lattice, no one has been able to enumerate polygons until now, and whoever does, if it is possible to enumerate polygons on the simple cubic lattice, you will have automatically solved exactly the 3D Ising model, which is considered one of the most important in the field. The mathematician Barry Sipra coined the term holy grail of statistical mechanics to refer to the 3D Ising model. So these problems are quite challenging. And Stefano mentioned at the beginning of the conference, the connection of hypergraphs to graphs and hypergraphs to many body problems. So there are many reasons to study polygon enumeration. This figure, so let me motivate the problem at least in 2 dimensions a little bit. So this figure is taken from a well-known book by Feynman about statistical mechanics. And in this chapter of the book, he gives an exact solution of the 2-dimensional Ising model by counting polygons on the square lattice. And in this particular chapter, the way Feynman does this is by using a random walk over the lattice to count these polygons. This is not the method that I will be showing today, but this is the random walk method is a well-known tool for counting graphs on lattices. Now, there are other kinds of graphs that you can draw on a lattice. For example, this is a spanning tree. That is a tree that visits every node. And for many years, it was believed that the enumeration of spanning trees and polygons, they were related problems. It was known that at a certain particular value of the temperature parameter in the Ising model, the polygons and the spanning trees generated have a certain connection. But they were considered to be separate problems. And what I'd like to show as a appetizer is that they're actually more closely related than they seem. So this is Onsager's famous solution of the 2-dimensional Ising model. It cannot be evaluated explicitly in terms of elementary functions or elliptic integrals and so on. Z is the partition function, but this partition function can be explicitly evaluated in terms of a hypergeometric series. I won't define what the hypergeometric function is, but it's a well-known function. And when I put this expression first on arXiv before it was published, this was exactly 10 years ago, Larry Glasser, who had worked with Lars Onsager, actually wrote me an email saying that Onsager and himself arrived at a very similar expression in the 70s that they didn't publish. Back then, there was not much interest in publishing these kinds of results. And so I was very curious, and it turns out the 2 expressions are identical. They are related by a hypergeometric identity. But can we gain anything from this kind of gymnastics? And the answer is we can, because now we know that the enumeration of polygons for the Ising model is exactly connected to the enumeration of spanning trees, and they're actually the same problem but disguised in different ways. So now I'm going to talk about the 3D problem, but I need to introduce Grassmann variables, because this is the what I consider to be the easiest and quickest way to do enumeration. So Onsager's original paper was more than 30 pages long, with many pages of algebra in order to reach his famous solution. Now, using Grassmann variables, the same calculation can be done in less than 1 page. So Grassmann variables are basically anti-commuting variables for our purposes. Grassmann himself was a linguist, and he was a self-taught mathematician, and yet his contributions today are spectacular. We have all kinds of objects named in his honor, like Grassmannian manifold and so forth. But the key property is that Grassmann variables anti-commute, so eta I, eta j is minus eta j, eta I, so the anti-commutator is 0. Now, if you look at the anti-commutator of an object with itself, it will be 2 times the square of that variable. But if it's 0, that means that eta squared must be 0. So the power of any Grassmann variable to the power 2 or 3 or 4, any power of the Grassmann variable is 0. And so this property is perfect for counting fermionic states. So it's very much used in the for calculating many body problems with fermions. Now, the integral of a Grassmann variable can be defined very simply. The integral is only 0 or 1. So if the Grassmann variable is there, so the integral of eta d eta, this is 1. And if it is not there, so just the integral of d eta but without the eta, then it's 0. And it's very simple to derive these rules simply using translation invariance of the integral and linearity properties. The physicists who derived these rules that I just mentioned for Grassmann integration, his name was Felix Berezin. He was a Soviet physicist who is perhaps who gave some of the biggest contributions to supersymmetry, superalgebra, supermathematics, and so forth. And he generalized Feynman's path integral for bosons for fermions. So the integral of Grassmann variables can be immediately used for exact enumeration for the following reason. Let's say you have this Grassmann action S, which is some collection of Grassmann variables, and then you exponentiate it, and you expand this exponential in a Taylor series. And then you do this Grassmann integration, like I said, if the variable is there, it's 1. If it's not there, it's 0. And then you also have this nilpotence property. What you'll find is that this integral calculates every single possible combination of those objects. So you can do the exact enumeration. This is the one possible way to choose the Grassmann variables for the two-dimensional Ising model. Let me just go over it very quickly. I don't have the time. How much time? So these black dots are the center of the square lattice, and I've put 4 Grassmann variables per site. So in the horizontal direction, I have this magenta and red Grassmann variables, and in the vertical direction, I have the green and the blue Grassmann variables. And I define this action in equation 1, the two-dimensional Ising model Grassmann action, which has one term with these weights u. U is a low temperature variable of the Ising model to count domain wall boundaries. But we don't need to know that for this calculation. And then you have the corner terms and what they call the monomer terms. So the monomer terms, which is this over here, are basically the magenta followed by the red and the green followed by the blue. And so you can fill the entire site with these pairs of monomer terms. You also have the corner terms, which will be green, magenta, magenta, blue, blue, red, and red, green. And finally, you have the term that counts the actual edges between sites for the Ising model boundary domain walls. So is this term over here, and that is this edge over here. So red, magenta, and blue, green. Now notice that all terms are quadratic in the Grassmann variables. So this action is a quadratic action. And when you exponentiate a quadratic form, you basically have a multivariate Gaussian, right? And the integral of Gaussians is very well known. It's a Gaussian integral, and we have determinant formulas for calculating Gaussian integrals. So the solution is very, very easy. Like I said, less than half a page of algebra and you recover Onsager's solution. And if you want the generating function for the polygons themselves, you can actually do the integration and find this result for the exact polygon enumeration on the square lattice. So this is a summary of So these results are quite old. This action over here was published by Stuart Samuel in 1980. Okay. What about 3 dimensions? Okay. So these are some polygons in 3 dimensions using the definition of polygon. And you can have planar polygons in 3D, but you can, for example, this purple polygon over here is a non-planar polygon. And the enumeration of these polygons is considered an extremely challenging problem. What can we say about the enumeration of these polygons? If you have any questions, please interrupt.
Okay, in a few last slides, you show a easy model generalization, I think, but I didn't understand. Yeah, that one. I didn't understand why you have four states. I mean, so you are generating more states through. I don't understand. Can you explain that to me?
Good question. Good question. Yeah, I didn't want to give too many details, but I will answer your question, and later I can show all the details after my talk.
Okay.
So you have 2 kinds of edges. You have this horizontal edge, and you have vertical edges. So we need to count these. And each edge has 2 endpoints, right? You have the left end and the right end for this horizontal edge. And for this vertical edge, you have the bottom edge, a bottom node and the top node. So we need to be able to count all these endpoints of the edges. So you have 2 horizontal Grassmann variables for the horizontal edge and 2 endpoints on the for the vertical one also. So we need 4 Grassmann variables per site.
Okay, so do you have 4 stages because it's a bidimensional model?
Yeah, it's actually 4 variables.
The
number of states is much higher.
Yeah,
it's 2 states per spin, right? If you have the Ising model spin, it's 2 states per spin.
Okay, better now. Thank you.
Okay, so going back to the 3-dimensional case, this is considered an extremely difficult and important problem, an unsolved problem. So what can we say about the 3D model? Like I said, Berezin, maybe I didn't say it, but Berezin actually solved the 2-dimensional model maybe more than 10 years before Samuel in 1969. But he was a Soviet physicist and he published his paper in Soviet journals. And so his work only came to my attention actually after I published some of these papers. So I was very excited to see that Berezin himself had solved the 2D Ising model. Now let's look at the 3D case. This was 1969, but the 3D case is still open. Even in 3 dimensions, edges of a graph, including polygons, non-planar polygons, they only have 2 edges. I mean, each edge only has 2 endpoints, is what I meant. And so if we follow our intuition, like I just answered now about this question about the Y4 Grassmann variables, if you put 1 Grassmann variable on each endpoint of the edge, you only have 2 Grassmann variables per edge. So we expect that the full Grassmann action can also be constructed again in terms of pairwise interactions, 2 Grassmann variables per edge. And yet, we're now in 2025 and there has been no success in finding this quadratic Grassmann action. And no Grassmann action was known at all until very recently. I will show you the recent result. So how can we approach this? So let us define for the Ising model this low temperature variable u equals exponential of minus beta t. K is beta times the beta times j. Beta is 1 over kt, the Boltzmann weight. And j is the coupling of the Ising model. So this K is called the reduced temperature. It's just so we don't have to carry the temperature and the J. And this T is the high temperature variable, which I think is a form which is more familiar in the field of hypergraphs. But the important point is that the Ising model can be formulated in terms of the high temperature variable and also in terms of the low temperature variable. So in terms of the high temperature variable, in any dimension on a square or cubic or hypercubic grid lattice, the partition function can be expanded in terms of the generating function of polygons. In the low temperature formulation, it can be expanded in terms of the generating function of domain walls. So in 2 dimensions, that's also a polygon, which is why the 2D Ising model is self-dual. But in 3 dimensions, domain walls are closed surfaces. So this is a generating function of closed surfaces, domain wall enumeration, and this is polygon enumeration. This has been well known for many decades. But what I did was simply obtain one in terms of the other, and then use a well-known result, also due to Stuart Samuel from long ago. This is from 1980. Samuel showed how to count closed surfaces on the simple cubic lattice. You need 12 Grassmann variables. I won't go into the details. And most importantly, you need quartic interactions. So pairwise interactions are not enough. These are the surfaces of the closed surface. These are called plaquettes. They have 4 Grassmann variables. So you have one in the YZ plane, one in the XZ plane, and one in the ZY plane. The action itself is this complicated thing. Again, you have the quadratic terms, which are the corner and monomer terms, and then you have the edge, or rather plaquette terms, which are quartic, and the full action has the quartic term plus the quadratic term, which makes sense because you need to count these plaquettes. It is not possible to count these closed surfaces with only pairwise interactions. So I have the action for the closed surfaces, and I have a connection between the generating function for polygons and the generating function for closed surfaces. So all we have to do now is to plug it in. I will save you the algebra, and we come to the main result, which is the action for counting polygons in 3 dimensions. So in other words, this will give you polygons on the simple cubic lattice. Now, of course, it's not too much of an advance because you can't do anything with this because it's quartic and there's no known simple formula for calculating integrals of exponentials of quartic forms, unlike quadratic forms. It's not a Gaussian integral, it's exponential of a quartic power, so we don't know how to solve this. However, what is fascinating is that a quartic term appears even for counting polygons. See, polygons the edges only have 2 endpoints, and yet a hypergraph seems to be underlying the graph. So in order to count polygons, you must count these plaquettes. You need to count plaquette closed surfaces. So this was the surprising result. And for example, one of the referees raised a very good question. The referee was very encouraging and positive, but the referee asked, but can we be sure that there is another action which is quadratic which will count the polygons? And of course, this is an open question, and certainly whoever answers this question will have made a big contribution to this question. So I will end here. To count polygons, you apparently, and I say apparently because we don't have a proof, there's no quadratic action, but apparently you need to count order 4 interactions. Thank you.
Thank you. So questions? So I have a curiosity. So now what would be your first step forward in this problem? What we will do now?
Oh, I think this is a dead end.
But maybe Sharo has some.
Just a couple of comments more than question, maybe question. I don't know even how to call them. One is a curiosity. What if you go instead to lattices in 4 dimensions? Do you expect to have still an extra power of 2, basically?
Yes. Very good question.
And the
Very good
second
question.
thing is, but the quartic form you showed us at the end, doesn't it look like a Lagrangian of a supersymmetric Higgs boson? Or am I wrong? I don't remember it. I think like it was something like this, but I'm not sure.
Okay, so about the Higgs boson, I don't remember.
Supersymmetric one.
Yeah, I don't remember. So, but I will look into this. And about the four dimensions, Massimo Ostili, who wanted to be here but wasn't able to, he's now a professor he's from Italy, but he's in Salvador, in Bahia. He generalized this result to all dimensions. So this came out more recently, but I didn't want to show it here because there are even more Grassmann variables. It scales very rapidly because you have to go to a tesseract, right? So, and then it scales very. Yeah, Massimo is from Rome. Yeah, Massimo is from Rome.
Supersymmetric king.
Other questions from the audience? If not, let's thank Gandhi again for the great talk.
Thank you.
So now we have the coffee break, and